Point I stopped yesterday. To make a quick summary, yesterday we saw how to construct vector spaces for our constitutive laws in the first time, and in the second time we get to look at the matter with their symmetry and the link that is between symmetry of the matter and the symmetry of the physical law. And in our context, physical law means tensorial law, because we are just in a linear framework, and so we are not looking for anything related to nonlinear behavior. So I've been doing these two parts. Today we're gonna connect them and show, once you got a vector space for your constitutive behaviors, how this the transformation acting on tensor will give a particular structure to your vector space. And the study of this particular structure will give you all the information you need to determine the number of your symmetry classes and the type of your symmetry classes. To do that, we will break in a certain way our tensor space into a skeleton. And this skeleton will be the structure of everything related to anisotropy. And this skeleton is called harmonic decomposition due to links between the irreducible space involved in this decomposition and harmonic polynomial. So all this stuff are driven by group representation theory. And I will also give some practical example, but mostly in a two-dimensional framework. Why? Because, in fact, in 2D, all the transformations are very simple, so we can have a kind of graphic representation of what is going on. And this graphic representation could, in a certain way, after be extended to 3 dimensions. By the end of this last part, I will give you, for two-dimensional space, general result we obtain, some recipe, providing, once you know the structure of your linear behavior, all the classes of symmetry without doing any computation. So let's begin the journey. Okay, so we introduce invariant subspace in first time and move to our general results step by step. So something interesting is if you have a vector space and a group acting on this space, you can quickly understand that not all your points will transform in the same way. Some point will turn at a certain speed, other with other speed, and remaining point will not turn at all. Kind of trivial example, but very visual, is the action of the rotation on three-dimensional space. If you look the orbit of point, so the kind of trajectory of your point and the rotation, it will appear that all the points that are on the axis of rotation will remain invariant, while the points that are outside your axis of rotation will turn. In fact, for this specific action, our physical space F3 will decompose into two irreducible spaces. The space will be the line, and in direct sum, the plane. So the transformation on space implies that you may have a partition into different way of transformation. This example is kind of very simple, but there is another example as simple, and I think that everyone knows. It's the deviatory decomposition, which is the same idea, but not in a three-dimensional space, but this time in a six-dimensional one. So if I move to the next example, so now I will look at a three-dimensional rotation on the space of a symmetric second-order tensor. An element G will transform in the way we saw yesterday, with G, my rotation, acting as many times as I got legs on my tensor. So the question is any element within this vector space behave in the same way? If yes, this decomposition is irreducible. And if no, we can split our space. So everyone knows that you can draw any second-order symmetric tensor in that way. You take traceless symmetrical parts, D or deviatory, and spherical part called S, which is a scalar that will multiply the identity. Okay, so here I look how this decomposition is transformed or not if I turn my tensor. The result is kind of very quick to obtain. My tensor, once transformed, can still be decomposed into a deviatory part called this time D star, and a spherical part called S. And this spherical part remain identical as in the first case. So what can be concluded on this example is that if I take element in my vector space, I will have some element that will not transform, while other element will be transformed in a different way. So something that can resume some of these things is that her decomposition is preserved by any three-dimensional rotation. If I take my tensor, transform it, and make the decomposition, or if I make the decomposition and turn my tensor, I will obtain the same result. So the space of symmetric second-order tensor can be written as two irreducible spaces that are in direct sum. I will call here H0, H like harmonic, the space of scalar, and H2, the space of deviator. The dimension is, in this case, the 3D case, because in 3D case is different. It's the order multiplied by 2 plus 1. So here it's 2 times 0 plus 1, it's a one-dimensional space. And here it's 2 times 2 plus 1, a five-dimensional space. This well-known decomposition into a deviatory plus spherical part can be generalized to any tensor. Okay, and if I look at the 2D situation, provided you take the right trace that is dependent on the dimension, the same things will happen. We will not irreducible spaces for 2D situation K at and the power is the power of the tensor. So for the 2D situation, my space P AG will decompose into a space of scalar, which will remain unidimensional, and a space of symmetric second-order tensor in dimension. And this time, the dimension of this space is 2 dimension. So if you add your components, you will obtain the dimension of 3, which is the dimension of any second-order symmetric tensor in 2 dimensions. Okay, that's some definition. Space is called irreducible if you cannot break it anymore, keeping the same properties. It's not okay. Very quickly, it's too written, but the idea is that this way of splitting tensor space into elementary building block can always be done. There is some well-documented literature in mathematics that sets the proper analysis of this decomposition. It's called the Peter-Weyl theorem that ensures you that if your dimension vector space is of finite dimension and the action on your space is made by a group which is compact, you can always split the space you are interested in into a finite sum of elementary pieces. This, for historic consideration, this analysis was, I think, the first time introduced by Backus in the 1970 in a beautiful paper which was dedicated to the analysis of the anisotropic elasticity tensor with regards to some application for geophysics. And this paper gets lost indeed for some years, and being exploited another time by the end of the 90s by Forte and Ganello in Milan, who used this for the first time, this decomposition, to obtain a rigorous proof of the fact that the space of elasticity tensor in 3 dimensions can be exactly split into 8 different classes. But while this analysis is remain mostly unknown in continuum mechanics, this field is well documented in the mathematics and very well used in the community of condensed matter physics. So it's another reference I put here, because you will have all the list by the end. It's GCB 78. It's Jaffanion, Shenla, and Bonneville, who show how you can investigate the property of your matters using this kind of analysis. This analysis is also very used in quantum mechanics. So what is a bit strange, it's the time it takes to reach the community of mechanicians. Okay. So here, I would say that harmonic tensor are the elementary building block of the tensor we are interested in with respect to rotation. So I give some characterization of the space in 2 and 3 dimensions. So it's the sum of things I just said. So I will call them h, k in 3 dimensions and k in 2 dimensions. what does it mean? If I take an harmonic tensor is of order k, the first point is it is a tensor of order k. So that's trivial, but that's a fact. The second point, I will take the third, in fact. The third point is being trustless. Okay, that's perfect. When people try usually to extend the debitoric decomposition, everyone think about the need to be traceless. But the second point is often forgotten in the mechanical community, and you should also be symmetric with respect to all the permutation of your indexes. If the tensors that satisfy these three characteristics are harmonic tensor A and Howard building block. And for the dimension, you got the two. In two dimension, any elementary representation are bidimensional, and in three dimension, every harmonic representation are three-dimensional. In fact, there is a deep link between in two-dimension the Fourier analysis of tensor, and here 2k plus 1 is the dimension of harmonic polynomial. Yeah.
I have a question. How do you define the trace of the one-order tensor?
Okay. Trace for me is an action to take one tensor of order n and to produce a tensor of order n minus 2. So traces are uniquely defined only for second-order tensor and for totally symmetric tensor. If you got a tensor of order n, you have got as many traces as the contraction you can do with the Kronecker tensor. Another point is you will say that a vector with just one leg is trustless, and a scalar is trustless. But for a third-order tensor completely symmetric, its truss will be a vector, just one leg. In the same ways, hk and k, according to the dimension, I will call them deviatoric and generalized deviatoric tensor. But in the literature, I think it's mainly not to pin. For them, deviatoric means trustless, no regard to any notion of irreducible decomposition. So the name is sometimes a bit fuzzy. But for me, deviatorics mean completely symmetric and trustless. Okay. So we'll focus mostly on the two-dimensional case. Okay, so here I will give some more detail on the irreducible space in two dimension. K0, it's a scalar, so you have not any transformation, it's remaining invariant. But you can also define another one-dimensional representation that is called K-1, and this one-dimensional representation is associated to the determinant of your transformation. In fact, it's a pseudo-scalar where we will change sign. If you put mirror operation, an element in K1, up will become down, and in mirror, down will become up. So this element, hemitropic element, so only invariant under a rotation and not a rotation and mirror, are associated to the notion of chirality. If you got in your decomposition a component in K1 minus 1, you will have something which is chiral, because the behavior in the mirror will be different. K1 is just the space of classical vector in two dimension. K2 is the classical space of deviators in two dimension. And for n greater, it will be space of extended deviator. why do k-dimension is a nice dimension? Because indeed we know how any elementary transformation will act on those irreducible space. If I took a rotation by angle theta, it will act on an irreducible space of order n as a rotation of n theta. If I turn my matter by an angle theta, all these different spaces will turn at different speeds. And the speed is proportional to the order of your tensor space. Okay? And in O2, we got also mirror operation. One representation for this mirror is just one component is mirror according to the x-axis. That's why we can represent the action in a very simple way. Here, I just represent an element K2. So, Elasticity Tensor in an adapted frame. If I turn and act by an angle theta on my data K2, it will be turned by an angle to theta. And in the same way, if I act on my deviator using a mirror, it will appear a mirror according to the x-axis. You will see the image in the mirror. So we can add a very intuitive representation of how things behave. And okay, so we can see if I act on elements of irreducible space, how this irreducible element will transform. Using this graphical representation, we will be able to determine in the first time symmetry class of elementary object. After, we will develop some more general results, but graphically you can see yet a lot of things. Something interesting is if you choose to represent one irreducible element. Here I just take an element in Kp, so an irreducible tensor of order P. I put him in a kind of a frame, adapted one, I just choose. But I can always find a rotation to fill its orientation. If I'm interested in the symmetry classes, I'm interested at the property modulo rotation. So here, if I represent an element, Kp, if I turn my tensor by an angle alpha over P, I will align my my element on the x-axis. So we can deduce graphically what are the symmetry classes of that element. Here, if I look at the, I will look at the symmetry group here. Okay, my generalized vector turn at P times the angle of rotation. So if I act on him with the action of Z2, ZP, it's a transformation associated to an angle theta of 2P. Okay. So if I make act G theta on an element Kp, this element will turn with an angle it's multiplied by p, so by due to the fact that your rotation is implied by the order of the tensor space, my element Kg is invariant by the group of rotation Zp. So it will turn my elements and put in the same position. In the same way, once in this position, you have a symmetry with respect to the mirror, with respect to the x-axis. So it can be concluded by this analysis that if the norm of Kp is different of 0, its symmetry classes is directly the diagonal group at with order p, and the other possibility is if the norm of my vector is new. In such a case, no vector is left invariant by any transformation. So that's defined graphically. We can define it another way. What are the symmetry classes associated to any one of those spaces? If I look, so here this symbol means the symmetry classes of the space in parentheses. So the symmetry classes of scalar is just the whole group of transformation. The symmetry classes of a pseudo-scalar will be just the rotation if this pseudo-scalar is different from 0, or the full group of rotation if the pseudo-scalar equals 0. And in the same way, all elements in harmonic spaces of order greater or equal to 1 will be either in the classes diagonal with n element, n is the order space, provided the norm is not null, and if their norm is null, you will obtain an element which is invariant by whole rotation. Okay. So we can play too with this graphical rule. It's almost formal, but it's how to see things. We can play graphically to deduce what are the symmetry classes of this kind of representation. This representation, okay, we study a space that decomposes into K2. It's a direct sum and not a tensor product, so there is a typo. And K4. Okay, how can we deduce the symmetry classes of this space? Oh. So the solution I will make is given here. At the first time, I look for symmetry classes. So the answer is modulo 1 rotation. So at the first step, I can align the component living in K4 along the x-axis. Okay. So now, what is the operation that let this situation invariant? It will be all P transformation. That's 2 is acting on your system with through 2P on 2 angle of rotation. So acting in this way, the first vector will turn at 2 theta, so will reach the original position, and the other one will turn at 4 theta, so also reach its initial position. So the symmetry classes associated to that situation is it's the Z2 symmetry classes. Okay, but in that situation, we got the two vectors we are not aligned. So if I see the image in the mirror of that situation, it will differ. So the only solution to add something with which is also invariant by the Diedrol group is to align the K2 element and the K4 element. Your two elements are aligned. They will turn one at 2 theta and the other at 4 theta, and being invariant by mirror operation. So in such a case, in such a geometry configuration, your classes of symmetry is D2. Okay. Now I will look at the next iteration. Here it's the rotation in D4. You got the angle of rotation is P over 2. So P over 2 will imply that this vector will turn and make a rotation of 2P, while this one, K2, will make a rotation of P and arrive in this situation. So if you want to have something which is invariant by the Diedrol 4 group, we must have K2 equal to 0. So this situation, just defined by a component in the by deviator of order 4, is invariant by D4, so it's a tetragonal invariant. The last situation is my two components are 0, and this situation is the trivial one. You are fully isotropic. Okay. Why this example is important is that indeed we classify graphically the symmetry classes of the elasticity tensor, because in 2 dimensions the harmonic structure of the space of elasticity tensor is 2 elements in K0 and 1 element in K2 and 1 element in K4. The 2 elements in K0 are the Young modulus and the Poisson ratio, the lambda mu of the Lamé coefficient, or any invariance, isotropic invariant of your elasticity tensor. Okay, and if you sum the dimension, we got 2 scalar, one element in K2 that will give you 2 dimensions, and 1 element in K4 that gives you also 2 dimensions. So you will have a space of 6 dimensions, and that is the dimension of the space of elasticity tensor in 2 dimensions. So understanding how an elementary transformation acts on the different spaces in the harmonic decomposition, we can deduce the symmetry classes of the space we are interested in. Here it's made graphically, but we can sum up all these things in more directly usable theory. Okay, but reaching this point, the natural question is, okay, but how do you know that the space of elasticity tensor decomposes in this way? Okay, natural. And okay, this decomposition is here it's modulo 1 and an isomorphism, but what is the explicit decomposition associated to that? So here I will move to the first point. Okay, I deduce that the harmonic contained in my tensor space are those one and not other one. Okay, here just some notation, but that's not very complicated. I will write the decomposition of the tensor, maybe in that way indicated other tensor, that's not very important, in the following way, by the big sum ranging from k minus 1, which is the space of Sonder's scalar, to the space of the tensor I decompose in this way. H is k in that case. That's way. Here, it's all the tensors that are involved in my decomposition, the tensor space that are involved in my decomposition, together with their order, and alpha k is the multiplicity of the elements of the same type. If I got something that can be written for the elasticity tensor, I got something like that. Just notation. I put a flat to say we are in two dimension. Things are k 0 plus k 0 plus k 2 plus k 4. And to shorten this notation, I will write, as this space is involved 2 times, I will just write 2 to shorten my notation. That is a practical example of what is contained. Okay, so doing that, we got alpha 0 equal to alpha 2 equal 1 and alpha 4 equal 1. Something which is important to say is that when I wrote this, it's not an equality, it's kind of it's an isomorphism. So you know that there is a way to take these elements and to make, knowing each element separately, one elasticity tensor out of these elements. But the way of constructual elements is another operation, and you should have to determine the isomorphism that can realize the decomposition. And usually, generally, this isomorphism is not unique. The only condition to have unique isomorphism is to have value alpha k equal to 0 or 1. Since you will have 2 spaces of the same type, your decomposition will not be uniquely defined. This can be seen readily on the structure of the elasticity tensor, because you got 2 spaces of scalar. You got 2 spaces for your isotropic coefficient, and you know that there is no unicity in the definition of isotropic coefficient for the elasticity tensor. You can choose any couple you want, Lamé parameter, Young modulus, Poisson ratio, and all the linear combination of these 2 elements, the one you prefer. So generally, don't have a unique way to realize your decomposition. Okay. Well, that's what is written here. You don't have a unique way to realize your decomposition, and it can be very difficult to realize this decomposition. For the elasticity tensor, it's quite easy. Okay, we got 4 different elements, and doing some algebra, we can manage to do it. But if you take some higher order tensor, like the 6th order tensor involved in strain gradient elasticity or even higher on the tensor, the number of elementary pieces will increase very quickly. For example, the second order elasticity tensor of mean-length strain gradient elasticity is so one typical element is T A G K and with the small symmetry here and here and the great symmetry by the permutation of the underlying block. Okay, the number of elementary pieces contained in this guy is 13. So to realize your decomposition with 13 elements is much more difficult things. And it's 13 elements in 2 dimensions. If you do the same thing in 3 dimensions, it's almost not impossible. I think this is possible in this case, but it's become very quickly difficult to handle the situation. But what is interesting is the following fact. Most of the properties of we are interested in, that means the number of classes and the type of classes, are totally independent on the choice of a particular decomposition. The only thing that is interesting, important to understand the number, the type of anisotropy you have, is just contained in the structure of your space, not in a particular way to realize the decomposition. If you know how to determine the structure of your space, everything is known. And you can, in second time, try to obtain one explicit decomposition. But it's useless in practice to have this decomposition to obtain a result. So we will try to avoid the computation of one explicit decomposition. And furthermore, because the computation of the structure is almost a direct operation. You can do it in a free line of calculus. So, how do you do it here? It seems to be a bit complicated, but I will illustrate any operation on the blackboard in order to see how the things are work in action. The idea is not to decompose your tensor space, but to compose it. We know that tensor space can be decomposed into irreducible representation. Okay, but there is a rule called the Clerk-Gordon rule that gives you the way that you can multiply your space and what is the result of the decomposition of the space. So you can construct using these different rules. You can compose quickly. You can determine quickly the structure of any tensor space. So we can see. I will make a back and forth here. Okay. Okay, I will do the example. So here we are interested in the space of Elasticity Tensor in 2 dimensions. This space, that's why I spent time in my first lecture on this topic, is constructed as the symmetric product of the symmetric product of R2. Okay. So, what is this? This is e.g. the space of symmetric second-order tensor, which is S2. Okay, so this can be written here 2 is just a vector, and here S2 is the symmetric tensor product of a vector with himself, as it is the symmetric tensor product. So here I got the rule to compute what is contained in the symmetric tensor product of 2 irreducible representations. So this can be written that way, because K1 is the space of vector, and so I have to use the rule symmetric tensor product of K1. Okay. The answer is you got K2 plus K0. And what is the meaning of that? We obtain here this deviatory, the spheric tensor space completed by K2, which is the space of deviatory tensor. So here it's the classical decomposition of a symmetric second-order tensor into a deviator and a spherical part. Okay, now what interests me is how you determine the structure of your elasticity. So the structure of elasticity is just S2 of this this product, this decomposition. So I'm looking for the decomposition of the symmetric product of 2 second-order symmetric tensor. That was done by an elasticity tensor. I can keep an eye on I invite to okay, here. So the next step is, okay, now S2 K0 spherical parts plus deviatory parts. Okay, this I can decompose. I give the formula. This is equal to the symmetric product of K0 plus the symmetric product of K2 plus symmetric product, non-symmetric product of K0 and K2. That is it's a tensor product. So I got a free term, and it's kind of very quickly to using this rule to compute this term. Here it's S2 of K0 with K0, so it gives you K0. Here it's S2 of K2, and it will give you so K4 using this rule again, K4 and K0. And the remaining one is 2 space with different orders, so I have to give a look here. And K0 and Kn, okay, it's Kn. So here, I'll obtain K2. Okay, so if I put them together, I retrieve in 3 lines the structure of my elasticity tensor in 2 dimensions. I can proceed the same way for the strain second-order elasticity tensor, which is a 6-order tensor, but it will take me 1 more line, and not the 10 pages of heavy computation. So that's very, very easy way to obtain the structure of the constitutive law you are interested in. No, that's called Petron rule, and the same exists for all kinds of group representation. You got categorical rule also for 3-dimensional representation, rotation, and it's widely used in quantum mechanics, this kind of. This one? Okay. In fact, there is a formula that explains it to you. But if you you make a symmetric product of two things. If you put it in matricial form, it will be evident that you will have a block that will link K0 with himself. Here, it's something like a symmetric matrix. So you got a block that links K0 with K0 in symmetric way. You got a block that links K2 with K2 in symmetric way. And you will add an extra diagonal block here that will couple K0 and K2.
For example, why is not there like K2, K0? Why only K0, K2?
Yeah, it's the transpose. So in terms of dimension, as you got something symmetric, if you got the upper parts, you got the...
Okay, so I can put it there, but it will not change the rest.
No, no. In terms of dimension of vector space, it's the same. But if my product here was not symmetric, just a standard product, I should have K0, K2, and K2, K0. You can really, it's a way to see it. I think it's a nice way to see it. Okay. The idea is kind of clear. It's that I got here K0, K2. This is not this very formal notation. Should not be try to analyze it too much. But doing the symmetric product, I will here obtain S K0. Here it's the application for symmetric application from K0 to K0. Here it will be we will have a symmetric application for K2 to K2, and here got something like that. And as it is symmetric, once you know it will be an operator M, and here you will have M transpose. So, provided you know that guy, you know the other one. Or it can be proved in a rigorous way. I think I give the reference.
But if you look into the table,
yeah,
and K2, K0, there is an empty.
Huh? Oh, here it's not empty here. It's the symmetric.
Okay.
But just kind of typical. Okay, so it's not a situation. Okay, if I spend some more time in this structure, so here it's so the structure of Elasticity Tensor into dimension. One way to obtain the explicit decomposition is this one. If you give me two scalar, one derivative of order 2 and one derivative of order 4, the isomorphism that will take those four elements and put it into an elasticity tensor is given by the following formula. This formula is not unique because you can define some combination of lambda and etc. Something important is that what you can conclude for two-dimensional space, the harmonic decomposition in two-dimensional space is not the same as in three-dimensional space. Each physical space have their own decomposition. It's a pure exception that the number of isotropic coefficient be the same in 3 dimension and in 2 dimension. If you take the strain gradient elasticity, your 600 tensor will have 5 isotropic coefficient in 3D, but only 4 in 2 dimensions. So the dimension of space is important. Okay. So here another example, if you want to do the computation, it is the structure of the tensor involved in strain gradient elasticity in 2 dimensions. So you got, in this case, 13 different elements and not just 4. So the structure of this 6-order tensor is much more involved than the one for classical elasticity. I don't think that somebody write explicitly one type of decomposition, and you can see that you will have a lot of way to write this composition because the elements in K4 are not uniquely defined. You can write them into any linear transformation because this space you have two K4 space. Same way for the K2 space, which is pronounced 5 times. So the elements in this path are not uniquely defined, and the same for the isotropic coefficients. And the other things that can be rid of directly from this decomposition is that you will have a space K6, and it is the space that will be responsible from the anisotropicity of your behavior for hexagonal cell. As you got this space K6, any hexagonal lattice for this linear operator will be anisotropic. So you can read off this information, and the other information that can be read off is that in your decomposition you have an element K-1. So it's an emitropic coefficient. If you got this element, the image of your behavior in the mirror will be different. So it's this presence shows that your behavior is chiral. You got chiral behavior, and in the classical elasticity, you don't have K-1 spaces. So classical elasticity is not chiral because of that, and strain gradient elasticity because of the space K-1 is chiral sensitive.
If you consider derivative of order 4, again you will avoid the K-1, no? I mean, the K-1 is related to the fact that there is 2 times 3 in this, or not?
No. If you take if you take the second order tensor with no index symmetry, you will have also a K-1.
I would say, no, wait, if it's 6 degree on the tensor, 8 degrees, you will have the K-1 or not?
In fact, I think the elasticity tensor is an exception. Yes, you will have, since the product of 2 third-order tensor, so this 6th-order tensor is the symmetric product of 2 third-order one. Since this case, since order 3, you will have -1 in any time. So the only situation that you will not have -1 is symmetric second-order tensor, so linear law between 2 vectors, and the elasticity tensor, symmetric linear law between 2 symmetric tensors. And after it's finished, you will always have chiral invariant, chiral sensitivity.
Even for the tensor of degree 3. For example, if this elasticity electricity, you will have the K-1.
Now, all of the tensors are different. You cannot have neither K0 and K-1 for all the other tensor. Or in fact, every even order tensor will only contain even power of harmonic space with even power. And all of the tensor will only contain harmonic space without the tensor. But that is true only in 2 dimensions. That is perfectly wrong in 3 dimensions. But the structure of the decomposition is very specific in 2 dimensions. Okay. So here I give some other structure that can be easily computed, which you can find in the literature. Quite how many time do I have? 10 minutes left? Okay. Okay. So I will skip some things, but that will be in my slides, so we can discuss it. We can discuss it outside this presentation. But once you got your decomposition, you know the number of coefficients you need in any classes, because you have some formula to compute the number of elements in any isotropic system. So I can obtain this present.
Can I have another question? Previously, before, where there is a D. For example, here, the DEGKL, could you explain a little bit more how it is graded in comparison to the other coefficients? I mean, because in general, if I could say CEGKL equals DEGKL, and I would left all the other things.
Okay, but D is completely symmetric and trustless.
And how do you grade it? That's the question. How is it? Yes.
Okay. How can I determine the structure? That's a big deal. In fact, there is an algorithm written by Spencer in the 70s that gave a process of construction. But this process of construction is not geometry. So you lose some information. If you do things properly, you should not make the harmonic decomposition directly. You got the first level of decomposition that will to split your tensor into kind of generalization of harmonic, of symmetric and antisymmetric. The first layer is to split a tensor into blocks in which indices will transform in the same way. So it will give you a first set of components. And you got operations that will put them in each one of these classes. And the next step is to take all this tensor and to remove the trace to obtain the harmonic one. But I avoid one big operation. Here,
so you mean, for instance, if I take CEGKL, I make the difference between isotropic, then between the tensor related to A, and then I will obtain D.
Yeah, D is kind of easy to obtain because you take your tensor C and you symmetrize him. If you symmetrize him, you will show that there is three inequivalent ways due to the index symmetry. You got three different ways to write C. So symmetrization of C is 1/3 this free permutation. Okay, so now you got a complete symmetric tensor, and you want it to be trustless. So there is just one trace. So you contract this complete symmetric, obtain the trust, and remove the trust, and you obtain it. In this case, it's simple. For more general situation, it's okay. So okay, back. I think it's okay. I think I don't have time to enter too much into details. But the only important thing is some general theorem that we obtain with one of my PhD students. That solves your problem in any case. So I just have to introduce two definitions here for even of the tensor and for pod of the tensor. So two different kinds. And it's the maximal set of classes. So here you saw that the maximum set of classes will be a Z, K, and DK ranging from 1 to P. So with this formula, you can obtain your sets. And it's slightly different for other tensors. So that's the maximal set you can obtain. It's almost a definition. Okay. So here, it's linked with the first part of my lecture. If your tensor is constituted tensor is constructed in this way, as the tensor product of two different tensors, one odd and one even, your set of symmetric classes is exactly this one. If you got here the symmetric product of two tensor space, here you can think about the space of 7 order, 6 order tensor of Milling strain gradient elasticity. Those spaces are constructed in this way. So symmetric product of spaces that are not completely symmetric. The classes of symmetry is maximum. So we try to identify this only for coordination due to the hypothesis we got constitutive tensor and not a general tensor. And we got every situation called in this rule. So I can obtain, if I look at, for example, the coupling tensor and the Milling strain gradient elasticity, this tensor got this structure. Okay, this structure is of that type. Tensor of the 2 and the tensor of the 3. So Q1 and P1. So I will have the maximum amount of symmetry, minus 1, and the minus is to distribute with Z high. And if we make a computation, I obtain at the end that all the symmetry classes for my the fifth order elasticity, coupling elasticity tensor of Milling strain gradient elasticity, together with all the dimensions associated to this case. Yeah, we got the same thing. Here, yes, here represents the result in 2D, but we also obtain the same result in 3 dimensions for odd order tensor and even order tensor. Okay, and to conclude, beside just general results, we are able to explicitly determine all the structure of the constitutive operator. Here is the 14 different cases of strain gradient elasticity symmetries you can obtain into 2D with all the different coupling you may have. And here it's kind of generic shape, but in each case we got the explicit representation of the elements involved in any one of these cases. Here I just gave an example for 6 order tensor that is hemitropic. That is just invariant by rotation, infinite order rotation, but not invariant by mirror symmetry. The non-invariance by mirror symmetry can be seen here within the appearance, within the existence of a skew symmetric matrix that couple different directions. And if we look at the same for an isotropic material, their coefficient A15 will be set to 0. So I will mean that we got also constructive procedure to obtain all the tensor involved in different theories. Okay, I will stop to let some time to Arthur.